later than the webinar we are hosting now. So back to the topic on hand. If we look to the agenda of today, we have two very interesting subjects. From Texas Instruments point of view, they're going to compare GaN to other technologies and also how it can increase power density to shrink your design. From Würth Elektronik, we're going to talk about a little bit about isolated gate driver supply, EMC issues, and also a little bit about high current inductors around the GaN application. I'm not going to talk too much about that because the gentlemen can both introduce this much better than I can. So I will switch to Martin Seeker, who will kick off this presentation. You can share your screen, Martin.
Yes, perfect. Thanks a lot, Alex.
Welcome. Good luck.
Thank you. Yes, and also welcome from my side, and thanks a lot for joining today. Let's see if I can keep my webcam on the complete time. It's today quite hot in Belgium. Let's see if my my laptop will do that today or not. Yeah, as Alex said correctly, working as field application engineer for Texas Instruments in Belgium. And today I would like to give you an introduction presentation about our GaN portfolio and indeed show some examples how we can increase the power density and the efficiency in your power designs. Let's have a brief look at the agenda. Roughly what Alex mentioned before. We'll first start with a technology comparison just to get an understanding where we need to place GaN and also how GaN behaves versus silicon technologies. We'll have then a concrete design example with a 1 kilowatt PFC. And then in the next part, we will have a closer look at our portfolio and our devices. As a short teaser, our GaN devices are actually more than only a standalone FET, but more about that later. And then in the end of the presentation, I will also point you to some interesting companion components that can be for sure very beneficial in power applications. And with the summary, I will also give you some links to additional resources. If we now first compare GaN with our power topologies, we prepare the following chart where we can map them in the power and the frequency domain. First, we start with silicon and silicon superjunction MOSFETs, for sure one of the most known technology, got introduced to the market in the 1950s. And silicon, and then especially silicon superjunction MOSFETs, are normally targeting applications in the moderate power ranges, 10, 20 kilowatts, and with a switching frequency in the lower triple-digit switching frequency range. As next, we can put IGBT in front of that. IGBT stands for insulated gate bipolar transistor, and they got introduced to the market in the 1980s. And they're definitely a nice choice for high voltage applications and higher power applications that are in the higher kilowatt, if not even megawatt range. Compared to silicon and silicon superjunction, you will see, however, that the switching frequency is limited. We see normally IGBT running in power applications in the range of 10 or 20 kilowatt. Next, we can place actually our first wide bandgap technology, SiC, into this picture. They also target, the SiC technology also targets higher power levels in the hundreds of kilowatts for sure. And big advantage versus IGBT is that we can already push the switching frequency to higher frequencies. Here also certainly in the 100 kilohertz range as a rough indication. And yeah, that's already a very big advantage versus IGBT. And now let's put a GaN into the picture. From the power level perspective, we can also place it in the moderate power ranges, in the lower double-digit kilowatt. But now comparing it with silicon and silicon superjunction or SiC devices, you can certainly see that GaN is an interesting technology to drive the devices with a higher frequency in your power architecture. that will later on bring a lot of advantages, which we will discuss today. And you can certainly see them as a very interesting technology if you need to shrink your power design, increase the power density, and have also nice efficiency. Now let's have a look at some specific parameters from GaN and silicon devices. As a short refresher, on the left you see the schematic symbol of a FET device with 3 terminals, gate, source, and drain. And yeah, as it is with a lot of other things in the world of electronics, we will have, of course, a lot of non-ideal parasitics, and we will go through them individually in the next step. The first one is the gate capacitance and the gate charge. Basically, what you see here between gate and source. And what you see here, if you compare GaN with silicon, that we only have a 1 nanocoulomb gate charge versus 4 nanocoulomb for silicon devices. This will effectively help us to turn on and turn off our devices, or GaN in general, faster, which will bring you the advantage in your power topology to boost the switching frequency. And specifically for the FET, it also means that you will reduce your gate drive losses. As next one, we have the output capacitance or output charge. Also here, GaN has a big advantage over silicon. You can compare it with roughly 5 nanocoulomb versus 25 nanocoulomb from silicon. This will also help you with faster switching frequencies that can be interesting in your design. And also as a big advantage, what we will see also later a bit, is that it will reduce the switching losses, because this capacitance is then definitely in your power path from the power conversion. The next parameter is low RDS on. If you compare it with silicon, we will also have here a lower value, roughly 5 milliohm per square centimeter versus 10 from silicon. That will effectively mean, of course, we can reduce our conduction losses, or if you want to provide smaller devices, then of course we can shrink the devices as well. I mean, it's always a trade-off between efficiency and size. And last but not least is actually a very interesting one. Due to the fact that the GaN implementation does not have an PN junction in its structure, we will actually have not any reverse recovery losses. So you will very often see in power designs the term body diode, and that's actually a behavior, a parasitic behavior, that you will not see with GaN devices. We will see also the advantages of this in a real power design later in more detail. And also as a side note, it will reduce then certainly the ringing at the switch node, because that will then also be again in the power path, and it will also help you with improving the EMI performance. Now quickly touching the topic of higher switching frequency, what it means for losses or smaller designs. On the left side, you will see a graph where we show the device losses over frequency. We of course have the conduction loss element, which is already improved by a factor 2. But the switching losses that we will introduce later will actually increase with the switching frequency. And if you see now, for example, this point silicon and want to compare what can it bring for a GaN-based design, it gives actually now 2 interesting design options for the engineers. Either you can reduce the power losses and increase the efficiency of the design, or for the same losses, you can massively increase the switching frequency. And what that actually means in terms of passives, I wanted to show on the right a comparison that our team did. It was a 1 kilowatt isolated DCDC design that was initially on a silicon-based solution, 100 kilohertz. And if you boost it to 1 megahertz, GaN-based solution, we can actually massively reduce the size and the cost of our magnetics. So that's for the part of technology comparison. Now let's have a look at some PFC topologies. If you look at an 1 kilowatt PFC, you will certainly see normal diode bridge PFC very often. It is based on a full bridge rectification in the beginning and then a boost stage. The advantage of this topology is certainly that it's a lower cost. will also have a good EMI performance because you always have the ground connected with a diode to the AC neutral. The power density will be moderate, but definitely the efficiency will not be the highest. And we will see also the numbers of the losses in a bit. And since it's also no symmetrical power architecture, the heat will not be distributed evenly. As next one, definitely for power designs that go higher than 1 kilowatt, you will see a dual boost PFC more commonly. It's basically based on 2 individual boost stages. So we have an additional inductor and then basically 2 PFC stages. Now, what you also see in some designs that you have as rectification elements and diodes in the lower left in schematics, or now for this example, 2 actively switched FETs. The EMI performance, same as with the diode bridge PFC on the better end. The heat, on the other hand, is better distributed because it's a more symmetrical design. And certainly, since we do not have the full bridge, the efficiency will then also be better. Advantage or disadvantage of this topology is then, of course, the power density that will decrease because you have now a lot of components in your design. And last but not least, totem pole PFC. That's the technology or the topology that we want to see in more detail today. The power density will be better because you have less components. You can actually see it as a simplified version of the boost PFC. Efficiency will be higher, but we will also come back to that in a bit. The heat will be also distributed in a better way because it's quite a symmetrical approach. The only thing is that the EMI performance will be worse because of the voltage changes at this silicon half bridge. But now quickly refresher how this PFC actually works. We have within totem pole PFC actually 2 operation cycles, so to say. The first one is linked to the positive half cycle of the AC input. And in this, you will see that the lower silicon FET is continuously turned on. And the GaN FET for the second half bridge is now switched to charge the inductor. And the upper one will then be activated if you want to discharge the energy from the power inductor. And we have the same way around for the negative half cycle, where the higher silicon MOSFET is always turned on, and the pair of the GaN FETs will then switch to charge and discharge the inductor. And this will maybe also explain a tiny little bit why we only need GaN actually in 1 half bridge. If you remember, the silicon-based half bridge is actually only switching within 50 Hertz or the frequency from your line input. So from a technical aspect, it would actually not be required to have a fast switching FET here. On the other hand, since this is a hard switching power topology, GaN is actually very good in this perspective versus silicon or silicon carbide FETs, because we do not have any reverse recovery losses here, but that's also something that we will check in the next slide. When we want to compare now the power losses, we actually need to first understand which elements of power losses do we have. You will see on the left the representation of our half bridge. The conduction losses are, of course, very simple to calculate. It's going to be depending on the RMS on, but then also the square of the RMS current. The switching losses, on the other hand, are a little bit more complicated. We have actually 3 elements here that we will look in more detail. The first one is the IV overlap losses. That's basically when you switch your FETs. Then we have the output charge losses that are mainly driven from the output charge and the output capacitance, and then the reverse recovery losses that you will also have. But I think when you have a closer look at the equations, you will actually already maybe get an idea why GaN is better, because we have here the switching time, which can be increased with GaN. The output charge or output capacitance is lower with GaN, and we do not have any reverse recovery losses with GaN. But now let's see what it means actually in numbers. For the comparison, our team took 3 designs, and you will see also in the lower right corner the conditions for all 3 designs. So we chose, for example, superjunction FETs and GaN FETs both with 70 milliohms. All designs were switching with 100 kilohertz, and they were for the same conditions with 400 volt output and an output load capability of 1 kilowatt. When you see on the very left side, the diode bridge PFC, of course, will have huge power losses, mainly driven through the rectification diodes. If you compare those numbers then with the dual boost, so the second PFC stage topology that was discussed before, you will see that we already massively reduced those power losses, because instead of diodes in the return path or for the rectification, we have now FETs. And yeah, the rest of the losses will roughly be the same. I mean, we will have again a low side silicon superjunction FET, a high side silicon carbide diode, and yeah, all losses that we will get from that are then in the same ballpark. Before we have now a look at the power losses that you will see within totem pole, let's have a quick look actually at the idea if we only replace the superjunction FET with a GaN device. Because that's also something that you can do. You do not need to necessarily change the topology, but only upgrade the power FET, so to say. But there you will actually only see that we get maybe 10-12% better or lower power losses because of its unique features and the improved parameters versus the silicon superjunction. But that's actually not all what we can achieve and what we want to achieve. Now, as last column, you will see the power losses of a totem pole PFC, and there you will see massive differences. So first of all, we have to say that the conduction losses of the switching FETs will increase compared to the other topologies, but you also need to keep in mind that actually the conduction losses were previously split between the FET and the silicon carbide diode. So if you add those two and compare them with the 2 watts of the losses in the totem pole, this is actually also already a deduction of 1.5 watt. Then the same counts then again for the rectification. It will massively decrease versus the full bridge rectifiers from the previous dual diode bridge boost. And yeah, the other losses will then again moderately decrease versus the previous designs. And if this made you now curious, we invite you to check out our demonstrator that we also have with full design resources on our webpage. You can look at PMP 20873, and you will find schematics, test report, and Gerber files for this design. It's a 99% efficiency PFC design based on the GaN-based totem pole PFC. From a power density perspective versus a comparable superjunction to design, we actually increases by factor 2. And yeah, the design was very nice. It's running at 100 kilohertz, so definitely higher than what you can achieve with other designs. And the GaN switch for this design specifically is based on the LMG 3410. But to the individual part numbers and the portfolio in a bit. Now to be precise. So Texas Instruments actually announced the GaN portfolio, or the GaN devices in late 2018. And in the first step, we introduced 3 devices on the market. It was the LMG 341X family, starting with a 150 milliohm device, then 70 milliohm and 50 milliohm device. And then you will also find already our next generation of GaN devices with the 2 at the 3rd digit on our webpage as preview. And they will actually extend our portfolio down to 30 milliohm. And with this portfolio, we target a big variety of applications, power topologies, starting for an active clamp flyback, maybe 65, 100 watt, up to LLC stages, 400 till 3 kilowatt. and then more advanced bidirectional or multi-level power designs between 5 and 10, 15 kilowatts. But now let's have a look actually at our GaN devices in particular. And I teased you already up front a little bit, you get way more than a standalone FET. And that's what you see on the simplified block diagram. What Texas Instruments does is actually integrate as well the gate driver next to the GaN. That brings some advantages that we will discuss in a second, but certainly from a design aspect, it's a very easygoing implementation. From the input side, you can work with a normal digital PWM input, so you do not need any additional gate driver to that. Our device also works with an unregulated 12-volt power supply and has integrated an LDO and a buck boost stage for all the different voltage rails that we need to operate this device. You will also see a 5-volt output actually to get a couple of milliamp in case that you need to power an external circuitry, the digital isolators, for example, that might come in handy. And then on top, we also integrate a couple of protection and monitoring functionality. So typical temperature protection, under voltage lockout, but then also a high-speed overcurrent protection. Now quickly some words to the topic, why do we actually integrate the driver in our devices? On this slide, you see a traditional implementation, a discrete implementation. On the left with the driver and then a standalone FET. And if you see or have a look at the equivalent circuit that you will get with it, you will actually see that you have a lot of additional common source inductance and a gate drive inductance introduced to the system. And Andreas will cover this topic in more detail in the second part of the presentation. But in a nutshell, it will certainly bring some issues. It will maybe not allow you to switch the devices or the power stage in a frequency range that you want to have. And it will also certainly bring some ringing and overshoots potentially into the system. On the next slide, you will see the implementation with our TI GaN device. So we integrate the driver in the same package with the device, and it's only now the bonding wires between the devices that will certainly create a bit of parasitic inductance, but it is limited versus the discrete approach where you have still the package inductance, the pin inductance, and of course the inductance on the PCB. Then what does it all mean on the PCB? We did a nice comparison between our solution versus a discrete solution. Our GaN devices with integrated drivers come in an 8x8 millimeter package. And next to some external power, you actually have everything integrated and might only need the smaller passives around. If you compare this one now with a full discrete implementation, you see that the solution size will immediately be factor 3 if you have to take care of the driver, the isolated or the bias supply in general, and then not even taking the current sense for the protection, for example, in consideration. So all in all, it will bring you the technical advantages of driving the design in a more reliable and faster way, but it will also certainly help you to shrink the design and to achieve lower system costs. Now a quick introduction to the next generation of our devices. You will find them already, as mentioned, as a preview on our webpage. All in all, they have the same look and feel versus the first generation. So you will get next to the GaN FET also the integrated driver. It will be as easy as with the first generation to work with the devices, meaning standard PWM input, unregulated voltage input. Everything is generated internally. The 5-volt pin will give you now even up to 25 milliamps. So if you have more external circuitry, that will certainly help you in this case. Most of the protection and monitoring functionality stays the same. But what is now introduced is actually that we have a dedicated temperature pin that will give you the temperature indication of our device. So what did we do with this device? We integrated now also a temperature sensor at the die from the GaN, and you can read out the temperature with a PWM interface. That was the part for our GaN devices. Now let's have a look at some companions, because yeah, just having power MOSFETs on a PCB is maybe not directly working. So especially if we go to more advanced power topologies, we would like to invite you to check out our C2000 real-time MCU portfolio. It's a very nice combination with our GaN devices. We already talked about the advantages of GaN, so we'll not touch those. But quickly some words to the C2000 real-time MCUs. It's actually a very scalable family with 30-bit floating point DSPs, multi-core, single-core with additional accelerator, yes or no. And that could come in quite handy, especially if you have multi-phase topologies, multi-level topologies, where you also need a little bit more processing power. Next to that, the C2000 processors will actually have a very nice mix with analog peripheral. So you will get a set of 12 or 16-bit ADCs with 3.5 megasamples per second sampling speed. So everything what you need to accurately measure the voltage and current. And then since you also need to switch, of course, something, you will also find a nice set of high performance PWMs in there, so that the C2000, I think, rounds it up very nice. We also have a dedicated application note about this topic, how to work with TI GaN and C2000 in particular. You will find the link in the presentation. Now a quick word to data isolators, because that's for sure a specification or requirement in a lot of applications, that you will have some isolation between the power stage and the processing. Andreas will cover this topic also a little bit later, but in a nutshell, you need to look for data isolators with good CMTI performance, so common mode transient immunity. And as in first start, I think you can have a look at our ISO 77 family as a reinforced digital isolator. Next topic, also only a very short summary that will also be covered by the second part from Andreas. You also need some isolated bias supply for your power designs. And there will certainly be a lot of architectural decisions that you will need to make in the beginning. Do you want to work with one centralized isolated bias supply? Then you maybe want to rather look at a flyback-based system for more output power. But if you want to have individual power supplies per half bridge, for example, or per a GaN device, then you can normally find a good solution with a push-pull power supply based on our SN6505. Those are, for example, also on the EVMs from our devices. And already as a preview, our team also worked on another part for a discrete or a distributed power supply, actually an open loop LLC instead of a push-pull. That will also bring some advantages, but you will find also to this topic and the comparison of all three power designs more training material on our website. So that's the part of my presentation. Let's quickly go through a summary. So in the beginning, I compared GaN with other semiconductor technologies. We also went to the specific details of GaN versus silicon to understand why GaN has some advantages. In the next step, we had a closer look at a 1 kilowatt PFC. We compared different PFC topologies and discussed where we actually get the losses into the system and how GaN helps you to reduce those. The third part was about the portfolio from our GaN devices, but then we also had a closer look at a device to see what you actually will get with an LNG 3034. And last but not least, we quickly mentioned some interesting companion devices from Texas Instruments that you can always check out. If you want to learn more about GaN, we have an easy to remember webpage, ti.com/GaN. And there you will find a big summary of additional application notes, white papers. There will be also some more detailed training videos, also touching now topics that we did not cover today, for example, reliability with GaN, motor drive with GaN, or maybe also some multi-level topology power designs. And for a lot of our designs, you will also find a lot of reference designs where you get the full design reports, schematics, Gerber files, and so on. And we also have a set of GaN-based plug-in daughter cards that you can then plug into an power design like this, for example. With that, thanks a lot for tuning in and for listening, and feel free to certainly leave some questions in the Q&A section, and thanks a lot.
Thank you very much, Martin. Andreas is setting up his system right now. I just want to remind everyone that they can ask questions. I already have a few questions coming in the Q&A session, but everything you want to ask and never dare to, well, try today. So, Andreas, your screen is shared. Good luck.
Thank you very much, Alex. Thank you very much, Martin, for the brief and good introduction in this GaN topic. So what we're talking about today is the topics around the GaN devices TI and some other producers, manufacturers are producing. We are talking about the especially isolated gate drive supply, layouting, EMC, and special components to fulfill the requirements you need in this area. So Martin already mentioned it. Usually you work in the high voltage system, even if it's GaN or SiC with isolated gate drive. Why do we do this? First of all, of course, we would like to protect against electrical shock. Second is we would like to protect the control circuit on the low voltage side here. Then we would like to protect against EMI in especially high common mode transient immunity we would like to achieve. We will see this later. And additionally, we could easier control the high side FET because we need a higher gate source voltage than the voltage on the high voltage node is. So to fulfill this, you saw we need some isolated PWM drivers and we need some isolated auxiliary power supplies. And this looks easy at the first glance, but we have to take a closer look at it, why it's not so easy to achieve a good design for it. So we have to look first what kind of voltages or what voltage levels do we need to drive a GaN or a SiC FET. So for example, if you have a GaN device, usually if it's a GaN device without any internal drivers, you drive usually with 5 volt maximum gate source voltage. The devices can handle 6 to 7 volt at maximum, but you need to have some headroom for ringing due to the parasitic inductance in the gate loop and the gate driving system. And to save switch off, you can apply between 0 and -2 volt to secure the GaN or the SiC. In this case, the GaN FET is securely switched off. And because we see later we have some Miller effect, we can accidentally turn on the FET again, and then we have a shoot through in our half bridge. If we have a SiC instead of a GaN, as a lithium carbide device, then usually depending on the manufacturer, we switching between 15 and 20 volt maximum gate voltage. So we really need to go to the limit there because it's not a linear, it's a linear function of the gate voltage to the drain current. So we really need to go to the limit to switch very efficiently. And to save or to save switch off the system, in this case the SiC, we need approximately between 0 and -5 volt to secure the SiC FET is switched off. As Martin already mentioned, there are different topologies available for driving GaNs or SiCs, and all of them have advantages or disadvantages. As you can see here in this application example from TI, we have our transformators with the SM6501 in this case. So the advantage of this push-pull design, it's very cheap and unregulated fast solution, but the voltage on the output is directly dependent on the voltage on the input. So you need a very stable regulated input voltage to have a very clean and stable regulated output voltage because there's no feedback loop in the system. And the tight input voltage range means you need a for sure a pre-regulator there, so there must be a DCDC or another LDO to provide the clean voltage on the input of this system. And from the size perspective, in power density, there are better solutions, as we see in the next slides. If you would like to do a push-pull design, because there are advantages, especially on the price side, there are many, let's say, different transformers already available in different with different isolated requirements, from the, let's say, reinforced insulation to the basic insulation. Everything is there with different turn ratios to at least different input or output voltage like requirements. So there's no need to make a special part for yourself. There's always off-the-shelf products in this. And the product area is here the mid/PPTI push-pull transformers. As we already mentioned, there is some CMTI issue. What does it mean? You heard from Martin, with GaN devices and also with SiC devices, we have a very high dV to dt on the switch node and in the gate drive circuit. So that means if you have a very high dV to dt multiplied with an capacitance, and the capacitance here is the isolation barrier capacitance. So this means the transformer here for the auxiliary supply has a capacitance from primary to secondary, and also the PWM isolator has also some picofarads of parasitic capacitance between primary and secondary. And the higher this capacitance, the higher the displacement currents we get. And this means we got a very high common mode issue in this case, because these currents are referred to ground and they close back to the source of the noise source. And this means usually you need capacitances under 20 picofarad and below, depending on the switching frequency and depending on your dV to dt. Additionally, to the EMI problem, you can get a problem that your insulation material can degrade with the high common mode transient currents. So this could be also then an issue. So the goal is in designing a gate drive auxiliary supply to have a transformer with the lowest possible coupling capacity. And therefore, we made a new development, which was the origin of it was the FormulaE, because in FormulaE, we have switching frequencies in silicon carbide in inverters up to 150 kilohertz and with over 300 kilowatt of power. So this is a quite high switching frequency, higher than in normal e-cars, of course, but the trend is going higher and higher as the semiconductors are improving and the materials in magnetics also are improving. So in this design, we choose a flyback because we have different requirements than in normal industrial environment, let's say. The disadvantage of this design is with, for example, the LM5180 from Texas. It's an open loop flyback converter, which needs simply no optocoupler, which leads to a very compact and easy and also very cheap design in the end. It's a little bit more expensive and a little bit more complex than a push-pull design, but it provides you a very tight regulated output voltage. It has a wide input voltage range. In our case, it was 9 to 18 volts, which is a normal range for automotive. And you can it can provide you more than one output voltage level. So in this case, we can provide +15 and -4 to drive a SiC, or +5 and -2 for a GaN, for example. There are different turn ratios with different possibilities in the end. The main goal in developing this quite new transformer was to achieve the lowest possible interwinding capacitance. And this is very low. It's only 6.8 picofarads. And the transformer can handle up to 6 watts of power. And if you look at the case size, 6 watt with this small case and this small, very, very small interwinding capacitance, this is actually unique on the market. There's no other manufacturer who can provide a product who is comparable with this. So this is especially interesting for, let's say, high power GaN and high power SiC devices, where you can need more than only 1 watt, but more, because the switching, let's say the auxiliary, so gate drive power supply increases with the switching frequency and with the gate charge. And if you have bigger modules like the great SiC modules, which are used in high power applications, then you get big amount of gate capacitance, a big amount of gate capacitance, and big amount of gate charge, and therefore you need a higher power supply requirement there. And what we did then, we made a reference design together with, for example, the TI chip here. We have a very, very compact design, which is only 40 millimeter height and 27 millimeter long. And this is intended that the customer completely integrated in his PCB. So this not made for selling and connecting. That's made just for a reference design. The customer can take the Altium data or the Eagle data and completely integrate it in his PCB directly next to the SiC or GaN FET. And the advantage is we have a very high efficiency, higher than many other, let's say, topologies in this area. And we have a very tight output voltage regulation from the 15 volt range, for example, and the -4 here over the input voltage and over the power you see. It's quite good regulated for the small size. Another topic is then, if you're talking about isolated power supplies in general, but especially with GaN and SiC, we need take a closer look to common mode currents due to the high dV2dt in the systems. So in the example, in this flyback design, we integrate on the input a conventional wideband common mode choke, and on the output a three-phase common mode choke. This is important. This has three phases because the current must flow through the core back and forth. And if you do not integrate the common connection here, you will have immediately saturation of the common mode choke. So the whole current must flow through the core. Otherwise, you get a complete saturation of common mode chokes. And with this combination, we get a good CMTI immunity in combination with the small interwinding capacitance of this transformer here. And therefore, you get lower EMI problems in the measurement. And as we take a lot of care in EMI, we are famous for it a little bit. So we also, of course, did a complete measurement setup for this reference design at full power. And we see on the input, we integrate a small LC filter here with a MLC and a very small inductor to pass the conducted test. And the radiated was passed anyway because it's a very compact design and with very good layout. You can copy paste this then and you have no issues at the radiated system. And this was made without any shielding, of course. Usually designs with higher power are all shielded, so this is not an issue. Only the cable is then the issue because due to the conducted emissions, and with our system here, usually no problem. From a thermal aspect, we see the hottest area here are the RCD clamp of the flyback and the output rectification diodes. So everything is around at maximum 80 degrees, and this can handle over 175 degrees. The transformer itself can handle 130 degrees. So you can work at full power in ambient temperatures up to 80 degrees. There's no problem for this reference design and for your resulting PCB in the end as well. If you're talking about driving a discrete, not integrated like TI does in this example, if you have an external GaN FET and a discrete driver for it, then it's beneficial to split up the R on and R off of the gate drive. This means if you switch on the device, the current flows this way, and if you switch off, the current flows this way. So you can independently control the turn-off speed and the turn-on speed of the system. And this you can fine-tune your efficiency and your EMI a little bit. So many, let's say, modern drivers already provides 2 pins to drive, let's say, have separately an on path and an off path. But if you do not have this possibility, you can use a simple Schottky diode, which blocks the on current and only is open for the off current on the system. And from a layout point of view, as Martin already mentioned, the parasitic inductance will hurt you a lot the faster you switch, because this inductance in combination with high di2dt gives you a high voltage drop and a high frequency range. And this means you will get EMI problems and you will get an overshoot in your gate drive system. So the first point is then if you have a discrete part, you you need to use, if it's possible, a part with separated Kelvin connection source. So then you can connect the auxiliary gate drive supply, the COM pin from your middle pin of your transformer directly to the source Kelvin point of the SiC or GaN FET. And this means your gate drive inductance is minimized and is independently of the high switching node in to source inductance. This leads to lower gate drive problems. So what can it look like? Due to the Miller effect, we can have the phenomenon if you have a bad layout, which means we have a high inductance in the gate drive system, the Miller effect can accidentally turn on the other FET on the high side or on the low side, depending on who's switching at the moment. So this is something we would like to avoid. Therefore, we need a very low gate inductance. Low gate inductance means this voltage ring is lower in amplitude. And if you have a switch off voltage, this is not 0, but -2, you can get a little bit even lower here. And if you have some ringing, then it's not so dangerous that you directly turn on the GaN FET. So you have a little bit more headroom in the system. So this is something you simply need to take care of. And it's also very important to have completely symmetrical design from the high side and the low side. Then there's no difference in symmetrical here. For example, what I did with a colleague is 4 MHz GaN totem pole SiC driver. So there we combine the gallium nitride technology and the lithium carbide technology. We cannot go too much in detail, just I'll show you this for some layout examples. What we see here is from the high side, the auxiliary gate supply. We have here the digital isolator. We have some signal cleaning. Then we have the high-speed driver from Texas. It's the LMG 1210. It's at the moment the fastest available GaN driver at the market. With this GaN driver, we drive 2 discrete low voltage GaN FETs, and these GaN FETs driving the gate of a silicon carbide FET, so the design was up to, let's say, 200 volts and can handle up to 3-4 kV. It was just made to show what's possible in high frequency, because usually 4 megahertz is very, very high and not many people are switching this high switching. It was just to show what's possible and what can be made with this technology. From a layout point of view, what's interesting, we see here we have the transformer of the auxiliary supply. We have the digital isolator of the high side of the transformer for auxiliary supply on the low side, and the low side digital isolator. So from there to there, we provide a basic insulation for 800 volts working voltage. So it means we have around 5 or 6 millimeter creepage and clearance. And from the high side to the low side, we have only functional isolation. That's enough for this case. And what we see here, this is the functional isolation with just 1-2 millimeter. That's enough. When we look at if you look a closer look on the high-speed driver, we see this the LMG 1210. Then we see here for the LMG 1210, we have the power supply from the three-phase mode choke. We go over a filter, a pi filter, to not to, let's say, conduct the high frequency noise of the GaN switching into our VCC system. So we filter this a little bit. Then we have the high side GaN FET, the low side GaN FET. These both connected very close together, let's say only in 0.5 millimeter distance between it. And the gate drive is very small in length. We have 04, 02 resistors here with only 1-2 millimeter distance to the GaNs, And after the GaNs, we go to the gate drive resistors, and we go here then more to the SiC devices. As I said, these are the GaN resistors that turn on and turn on from the low side. And we have here the filter for the GaN drive in respect to the VCC, the plus 19 volts. And of course, we have a higher power loss due to the high switching frequency and the high currents here. For the gate drive resistors, for the SiC FETs, we need at least 2 or 3 watt types because of this, they are a little bit bigger then. If you are working with gallium nitride, you do not have, there's no reason to be afraid in the end, because many GaN devices or GaN reference designs, AC/DC reference design for USB-C chargers, 65 watt, for example, are GaN based actually, because they can achieve very high power density, but the switching frequency is not completely out of order there. So the legacy design is working with, for example, 70 kilohertz, the newer designs are usually not over 100 kilohertz on fundamental switching frequency. So, but if you have the problem that you got not only at switching frequency and the lower frequency range, common mode and differential mode EMC problems, but also in 10 megahertz or 100 megahertz, then some combination of nanocrystalline cores and air-gapped, this is especially air-gapped common mode chokes, can help you to get a very broadband and wideband filter. In this case, I made the simulation with LT-Spice. You see the schematic down here. We made here a common mode with common mode means in this case we have an LC filter which is formed from the Y capacitors and the common mode choke and another Y capacitors and the common mode choke. And with this combination, we achieve a very broadband filter effectively. And if you'd like to simulate this in differential mode, then we only look from the difference from the input side to the output side, and we clamp out a little bit this common mode range. And then we see also from 100 kilohertz to 100 megahertz, we have a very broadband working filter in this case. What I will tell you easily is if you would like to simulate, you will find all of our products usually in LT-Spice for simulation. It's a free tool. It can provide you a lot of simulation power if you want. For a roughly estimation, it's a good point. Why not? In this case, it was a 4 kilowatt design. So the current and the components are made for the maximum what is possible for one phase system. So 3 kilowatt, you cannot achieve more in usually, and it's working fine. And last month, or let's say last 2 years, many manufacturers from low voltage GaN devices are pushing them in the DC-DC market. I had a lot of questions from customers if this makes sense or not. Let's say that depends. They are very strong in marketing sometimes, and not every design makes sense, because many of these GaN devices cost 10 times more than silicon MOSFETs, and the benefit is often not 10 times more than the silicon MOSFET. So where are the fields which can this be beneficial for the customer? For example, if you need a very, very small duty cycle, this can be achieved with GaN, because you have a very, let's say, narrow turn on and turn off switching edge. So this means you can achieve a duty cycle even lower than 1%. And this can help you, for example, if you have a very, very high step down ratio. From example, you have a rail voltage from 48 volts, and you would go down in one stage, because of any reason, it's your design, you would go one stage down to 1.2 volts, and you need 20 amps for any kind of POL. So in this case, again, is in advance, because with a silicon, you usually cannot achieve this very small duty cycle, because the turn on and turn off times are too long then to get this in a very high frequency then. So, but if you see these reference designs from various manufacturers, they proclaim in the datasheet, of course, you can go 10 megahertz, 100 megahertz, but all of the reference designs are usually, let's say, still below 1 megahertz or maximum 2 megahertz. The reason is simply the efficiency. They, again, is good, but it's not a miracle in the end. So the higher the switching frequency, even with GaN, the higher the switching losses simply. So in this case, usually it's even beneficial you switch below 1 megahertz, but you can use the very sharp turn on and turn off to get this very high step down ratio there. And to help you there in this area, we developed a new inductor, which is very low in height, only 4.1 millimeter. It has then to be glued on the PCB to get a good mechanical vibration resistance. And it can handle a rated current up to nearly 40 amps and a saturation current of 33 amps. And the RDC is only 0.86 milliohm. And if you would like to know how much losses do you get with this, you can use the red expert. For example, I have put in here 48 volts down to 1.2 volts at 20 amps. The example here has a switching frequency of 500 kilohertz. The ripple current factor is 40%. Then you see if I select this new inductor with 1 microhenry, I get approximately a complete loss of 0.4 watts. The AC losses are in this case 50 milliwatts and the RDC losses are 350 milliwatts roughly. And the temperature rise of the inductor itself is around 12 Kelvin, which is more than safe. So even you can go even then to 30 amps is no problem with this. The only limit is then the saturation current of the part with 33 amps. But you can use Red Expert here to get a fast and easy approach to your design. And that's all from my side so far. Just for you as a summary, you see if you do an isolated gate drive, we have to take care a little bit more than normal designs, especially if you switch very fast due to the CMTI problem and the common mode current is your biggest enemy here. And take care of your interwinding capacitance of the digital isolator as well as the power transformator in the auxiliary supply. And in the end, you do not have to be afraid because of GaN, even not in low voltage DC-DC converters, but you have to simply follow a few rules. The layout is more critical because the switching edges are faster and therefore you get punished with a little bit inductance too much in your system. And that's all. Thank you for your attention and we are open then for the questions.
Thank you very much. Well, like Andrea said, we are open for questions. We have a few already in. So let's start there a little bit. Although I think the first one was already answered in the Q&A session and I think even in your presentation. The question was, what external measurements are necessary to become EMI compliant? Which is, of course, is a broad question.
It is very broad, yes. In the end, you have to do the same measurements like normal, so let's say silicium devices. As I said, maybe you get in some applications a little bit higher frequency content, but if you look at the most reference designs, the switching frequencies are not completely out of range. They're a little bit higher, but the focus for every manufacturer at the moment is to gain up the efficiency a little bit. In all the designs, efficiency is in focus to get the Energy Star compliant and so on. And this does not mean you get completely another EMI signature than before. It can be a little bit different, but the difference is not so huge, let's say.
So basically we can cover it with the existing EMI solutions.
Yeah, most of them. And as I said, at the moment, if you have AC/DC designs, you mainly use manganese zinc cores because their main EMI problems are below 1 megahertz. This will be in future the same at the moment with the current switching frequency with GaN. But if you have higher frequency content in your system, you can use common mode chokes with nickel zinc core in combination with manganese zinc, or you can use a nanocrystalline core or these air-gapped common mode chokes I showed you, for example.
Okay.
But the layout is most important is the layout in the system and the interwinding capacitance for the common mode.
Perhaps an interesting follow-up. He say an air-gapped common mode choke. What is the benefits to use that instead of a non-air-gapped common mode choke?
Yeah, the air-gapped common mode choke gives you the benefit that your at first glance the frequency range is much more broader. So if you look at the most common mode chokes, they have a very narrow, let's say, working frequency range. The air-gapped one has a working area, for example, from 1 megahertz up to 100 megahertz. The disadvantage is then the absolute attenuation is lower than with a manganese zinc because due to the air gap, the permeability of the whole system is smaller.
Okay, thank you very much. Then we had a second question, maybe even a statement. That's regarding your slide number 7. There it stated that the LCM on slide 7 doesn't work and will be saturated. So I mean that's the
Let me take a
commode
look
choke
what
there.
you mean. Number 7. That's right. This was this is simplified. I will show you again. Just a second. It's completely right. So
So
let
just
me see here. Just take a screen share.
just a little test, people, to see if you're paying attention.
Yeah. So
Yeah,
there
that's
we
it.
combined the both lines. There is L and N together in this, let's say, simplified schematic. You're completely right. It doesn't work. So if you took it more precise, we have, of course, like we did it here. There you see, you need to go through the whole current from plus back from minus needs to go through the same core. Otherwise, we have saturation. That's for sure.
That's true. I guess the first picture was coming from a marketing flyer.
Yeah, a little bit.
Perfect. And that's about all the questions I got in until now. So if you still have questions, oh, someone is saying something. Does the GaN options from TI have the same behavior when close to 600 volts? To rephrase, is there a dynamic RDS on behavior when the RDS on values increase as you approach the voltage limit? Complicated question. Martin, you still here?
Yes, I'm there, but Toby, can you take this one?
Tobin is also from TI. He is the product expert for this product portfolio, if I'm understanding. Are you here, Tobin? Perhaps something is wrong with his audio connection. So if you, is it okay, Jesse, if we approach you offline to answer this question? And we can continue with the rest. Okay. Not getting a reply from Tobin, so we will answer that offline, and that will summarize all the questions that have been asked has been answered. I want to thank you all for your attention. Hopefully you have learned something. If there's any questions left or you just want to have more information about the subject, please contact any one of us. We will try to help you in any way possible. And from my side, thank you very much for joining. Martin and Andreas, thank you for presenting, and hopefully see you next time.
Thank you very much, and have a good time.
Yeah, thanks a lot. Goodbye.
Goodbye.